Ozonolysis is a reaction that's usually covered along with all the other alkene reactions. But I think it really belongs more in the Diels-Alder section. So here, if I take an alkene and I react it with ozone, I usually get the ozone from an ozone generator that holds oxygen gas under a big electric charge. And so I'm generating ozone. Ozone's pretty dangerous, so I want to make sure it's pretty dilute and that kind of thing. But treat this alkene with ozone, an intermediate that is then worked up under reductive conditions, usually dimethyl sulfide, sometimes zinc. And the product has two new carbonyl groups in it. We're essentially chopping this pi bond in half and adding oxygens to the pi bond stumps. This also works if it's not part of a ring. So here I'm getting two products out when I chop that pi bond in half. And I really don't care about this one. Really, this is just a way for me to turn an alkene into an aldehyde with one less carbon in it. How does this work? This works the same way that the Diels-Alder reaction works, by orbital symmetry. The first step in ozonolysis is a concerted reaction. Ozone is a 4 pi electron system, just like a diene, and so the symmetry of this orbital is just like the symmetry of the highest occupied orbital in a diene. So your mechanism, your transition state looks just like your transition state for a Diels-Alder reaction. Just like the Diels-Alder, you're moving 3 arrows around and 6 electrons. And so what you end up with is a new cyclized system. It's not a 6 atom system, it's a 5 atom system this time. Sometimes we call this reaction a 3+2 because we're adding 3 atoms to 2 atoms. And we're getting something called a primary ozonide. Where that primary ozonide goes is an area of active research. We're not sometimes exactly sure what's happening. But the way you can think about is this obviously is very unstable, right? It's a cyclic peroxide, but worse. Those OO bonds are very weak. This thing can break up into these two components. This is a weird carbonyl oxide. A lot of times, if these are pretty unstable, this can just flip over and they can redo, do another cyclization to get to this, which is a little bit more stable than this. But either way, our reductive reagent is either going to come here or there and grab one of these oxygens, and dimethyl sulfide leaves as sulfoxide, so the sulfur takes that extra oxygen, and that's how we get these two carbonyl compounds safely. So again, the primary ozonide can bust apart and reform a new ring, but even that ring is not very stable. And we're going to need our reductive workup to get our carbonyl compounds that we want. Ozone addition to alkenes is just one example of a 3+2 cyclo addition. Again, similar to the Diels-Alder reaction, 6 electron concerted process. And there are lots of 1,3 dipoles that look like this. Again, ozone would fit under that category. Lots of compounds that look like this that can add to alkenes to give 5-membered rings. One more of those that I want to touch on because it's really useful in biochemistry, actually more so than organic synthesis, is an alkyne azide cyclization. So this is an azide. You've seen it a few times because azide's a great SN2 nucleophile, a good way to make amines. And this is an alkyne. So on your own, take a second and try to sketch out what an alkyne azide cyclization product should look like. Your product is a 1,2,3-triazole, and it looks like that. So for many years this was known as kind of one of many of these thermal cycloadditions, so you'd cook these two things together. Sometimes you need quite a bit of heat. Then it was discovered that a little bit of copper catalyst, copper-1 catalyst, can make this reaction go very, very quickly, very regioselectively, and very nicely. So a little bit of even copper wire sometimes can make this happen because there might be a little bit of copper-1 on the surface of the copper wire. So this is a great reaction in terms of yield, efficiency, and all that. The downside is that, do I really care about 1,2,3-triazoles? Do they show up in drugs? Oh, they show up in drugs a few times. But that's actually not why this reaction is important. Forget the word triazole for a second. Let's just think strategically. What this reaction gives us is a way to staple two things together, and that staple, that junction, is really, really stable. It's an aromatic ring. So let's say I've engineered some part of a cell, some organelle, or maybe even just some protein target. I've engineered it to express some kind of alkyne side chain. And let's say I've got some dye molecule, some fluorescent dye, or something that will light up like luciferin. And to that I've attached an azide molecule. Now both of these functional groups are actually surprisingly stable. They're not really going to react with anything else but each other. If I add a little bit of copper to the system, now I've got this really, really strong junction that essentially has tagged my biological target with some fluorescent or otherwise interesting molecule. Right? That's a really powerful technique, to just be able to attach two things, no matter what they are, to each other. And what makes it work, again, is that alkynes and azides really aren't going to react with anything else. So we can call it orthogonal chemistry, bioorthogonal chemistry. And if we don't like copper because copper is toxic, then we'll just think about other ways to engineer maybe strained or unstable alkynes that are much more likely to react with azides. So biochemists and people that are really interested in understanding how cells work have really latched on to this alkyne-azide coupling as a way to attach two kind of random big compounds. This reaction is sometimes referred to as the click reaction because it's like clicking a seatbelt. You have two reagents that come together, no leaving group, nothing is wasted, and as soon as it clicks together, it ain't coming apart. So mechanistically, it's a 3+2 cycloaddition, much like the diazole, or much like ozonolysis, kind of like the diazole. And practically, it's a great way to connect two things.